Problem 56 involves a ball being dropped to the floor and bouncing back up. It drops 1.5 meters and it rises 1.45 meters after colliding with the floor. Now, one important point that I made is simply that, let's say this is the ball here, okay? From the time the ball is released to the very instant at which it first encounters the floor, its acceleration is uniform, the acceleration of gravity. So that if we analyze this motion based on uniform acceleration, the final velocity of this ball is not zero when it hits the floor. Okay, the ball is moving at whatever velocity it develops up to the instant it touches the floor. Then the acceleration changes and your analysis for that phase of motion is over. Okay, so when we drop the ball 1.5 meters, we're going to assume an acceleration of 9.8 meters per second squared downward. And we've chosen arbitrarily, I let the class choose, they decided, well, we're going to let up be positive. Sometimes if we were just dropping the ball, it would make a certain amount of sense to let down be positive, because then we wouldn't have any negative signs. But since the ball is then going to be bouncing back up, it would be confusing to have down be positive and up be negative. So it's probably a better choice to let up be positive and keep it that way throughout the analysis of this entire situation, from the drop to the rebound. Okay, well, so from, again, release to first contact with floor before it's had a chance to slow down due to the acceleration it gets in contact with the floor. Initial velocity is going to be zero. Acceleration negative 9.8 meters per second squared, since up is positive and gravity pulls down. And displacement negative 1.5 meters, because from here to here is negative is a downward displacement, and since up is positive, that makes that downward displacement with this choice negative. So we can try to reason this out, we can try to pair things up, we can try to use definitions. We're not going to get anywhere. We're going to have to use the fourth equation of motion. Here that we're going to have to get into pretty convoluted reasoning from our definitions. And we really don't want to do that. Well, the fourth equation is easy enough to use. So we get Vf squared equals V naught squared plus 2a delta S. And we just take plus or minus the square root of the right-hand side. That's going to be our solution for Vf. And I've just got an etc. down there. You can plug the numbers in, take the square root, and I really hope that you put the units on every quantity. Verify that you have meters squared per second squared units for both of these quantities so you can add them. And then when you take the square root of the meters squared per second squared quantity, you'll get a meter per second quantity, which has units that match that of Vf. Okay? So, we have this, we can plug the quantities in, and we're going to choose the negative out of the plus minus. So we choose negative since the ball is descending. Okay? Now, that's going to give us a value for Vf. Now, we could then use V naught and Vf, since we now know Vf and we already knew V naught, and the delta S to find our delta T. But that wasn't asked in the question. It doesn't hurt to go ahead and find it. Reinforce the process for yourself a little bit, but it's not asked, and you wouldn't feel obligated to answer that question. Okay. Then, when it comes back up, okay, delta S is plus 1.45 meters, and that's pretty obvious. The final velocity is zero because, again, when something rises, it comes to rest at the top for an instant before falling back down. So, at the peak, its velocity is going to be zero, and the acceleration is still downward 9.8 meters per second squared. Upward is still a positive direction, so the delta S is up, the acceleration is down. And then we go back to the same equation, but this time, of course, it's V naught that we want and Vf that we know, so we have to solve the equation for V naught. Well, that's easily enough done. We subtract 2a delta S from both sides. We're going to get Vf squared minus 2a delta S on the left side and V naught squared on the right side. Now we're going to flip those sides around, so the V naught's over here, and we're going to take the square root so that we get plus or minus the square root of VF squared minus 2A delta S. And when we get our plus or minus result, we'll discard the negative in this case because we know that the object is starting out here with an upward, therefore positive velocity. Now the other thing, and this can be a little confusing, but what happens in contact with the floor? Well, the ball descends until it makes contact with the floor. Then it compresses. Now, a steel ball doesn't compress much, and it better be on a steel or some other hard floor, or it's not going to bounce back up for 1.45 meters. If it drops on a wood floor, it's just going to bounce a little bit. But on a hard steel floor, it'll bounce back pretty close to where it started. Okay, a lot like a super ball. Okay, well, it compresses. Now, it only compresses, probably in the order of tens of microns. I'm just making a guess. I haven't analyzed it. You've got to get all kinds of material properties and put them together to see what would happen. And then it's still a complicated analysis, well beyond anything you're going to be asked to do. But it just compresses at least a little bit, but it's really hard to compress steel, so there's a whole lot of force involved in that compression. And then when it springs back, it comes back up. So while it's in contact with the floor, the problem tells you that it's in contact for 0.08 of a millisecond, 0.08 milliseconds, which is 0.00008 seconds, or 8 times 10 to the negative fifth seconds. Okay, I'll write the 8 times 10 to the negative fifth. Seconds. And it's okay to write it out either way. If you get many more zeros, you're going to want to use the scientific notation. I just broke a piece of chalk. Okay. What do you know about the motion of the ball when it's in contact with the floor? Well, you don't know a lot. You really don't know how that compression develops, evolves, whatever. You don't know how that really goes. And you have to, again, do some very high-level analysis way beyond the scope of this course to determine it. So we just make the simple assumption that while in contact with the floor, the acceleration is uniform, so that we can use what we know at this point to analyze it. Okay? Now that's not a good assumption. It really isn't uniform. That force is kind of, if you graph the force versus time, it's got a peak and shape kind of like a Gaussian, and you don't need to know what that means. Just that that's not a real good assumption, but it still gives us a ballpark idea of how much force is involved in this process. Okay, so for that 8 times 10 to the negative fifth seconds, 800 thousandths of a second, 0.00008 seconds. What's our initial velocity and what's our final velocity? Okay, well, I say the initial velocity is the final velocity for the first interval. Okay, so put parentheses around that. So whatever we found for our final velocity up here will be the initial velocity for this interval. So this VF here gets brought down, bring it down here and all the way around, and it becomes, and I probably should have drawn the arrow to the V naught, lose the graceful arc of my curve, but that's still pretty graceful. Okay, there's our V naught for this interval, this 800 thousandth of a second interval. The VF for this interval is equal to V naught for the second interval. And that's done here. So this V naught here becomes this VF. Okay? Now we have an 800th of a second interval, a V naught, which is negative, the downward velocity we got in the first interval, and a VF, which is positive, the initial velocity we had for the second interval. If we put all that together, we can find the acceleration and if we want the distance through which the ball compresses. Now I urge you to complete this analysis. Once we have our initial and final velocity on this short interval, we can easily find our average velocity, our change in velocity, just by averaging or subtracting the velocities as appropriate. And we can take our change in velocity and combine it with our delta t to get our acceleration. Now, I said in passing that we could find the distance the ball compresses from this analysis. That's not quite true, because what we would find if we found our delta s, it would be the difference in the position of the ball at the beginning of this interval and at the end of this interval. And our V bar is going to be close to zero because this velocity is going to be downward, this velocity is going to be upward. Now this velocity is going to be a little less than this, and you can think about why. A little less in magnitude, a little less speed here than here. But if you average the positive and negative velocities that aren't very much different, you're going to get an average that is pretty close to zero. And you'll see that if you carry this through carefully. We could estimate, the problem doesn't ask for it, but think about this, we could estimate how far the ball compresses. Now this is just an estimate based on uniform acceleration, which is not really the case. And we're going to base that estimate, we could base that estimate on the idea that, okay, delta t for the entire compression and decompression between the time the ball first hits and the time it leaves the floor springing back is this 800 thousandths of a second. We can cut that in half and say, okay, well, about halfway through that interval, the ball should be at its maximum compression, and then it's going to decompress for the other half of the interval before leaving the floor. So that would be 400 thousandths of a second for the ball to come to rest. And having come to rest, it's going to be compressed by an amount equal to the distance it has traveled in that 400 thousandths of a second, starting with this velocity and ending up not at this velocity but at zero because it's coming to rest. So you could do another acceleration phase, a different acceleration phase, set up a different problem and determine essentially how far the ball compresses. And it might be interesting to do that. If you actually work this through, you'll have all the numbers you need to do it, so it shouldn't be very difficult to actually carry it through.